In Bezout's theorem, we want to show that if a and b are two numbers, integers, whose GCD is d, this is given, then we want to show that there are integers x and y such that ax plus by is equal to d. So the point is to establish the existence of x and y. Can you find such x and y always? Now I'll give you a sample problem on this. Suppose we have 230 and 421. Step 1 would be to find their GCD. So put it in the comment, or if you are in the Shinta portal, then put it in the quiz section. Then find x and y such that 230x is equal plus 421y is equal to d. So you have to first find d, then find x and y. First find d and then find x and y. You should be able to look at this in the quiz section if you are in the Chinta portal. Okay. Now, this is the main theorem, that there will always be such x and y such that ax plus by is equal to d. A sample example, we talked about this in the last class, that 15x plus 10y is equal to 5. GCD of 15 and 10 is 5, so we are using 5 here. And there are x and y which works. For example, x equals to 1, y equals to minus 1 will work. But then x equals to 2, x equals to 3, y equals to negative 4 will also work. Can you find some other examples of this solution? So find one more solution. Maybe you can put this in the comment or in the quiz section, wherever you are. Okay. How do we prove this? How to prove this? And this is very important because writing mathematics is one of the most important part of doing mathematics. So let's see how we can do this. We create a set. So create a set S which contains all the numbers of the form ax plus by such that ax plus by is greater than 0 and x and y are integers. So this is the set S. This symbol here is such that. This is the trick. You create a set of all possible ax plus by such that ax plus by is greater than 0. Before we proceed, let me explain to you what this actually means. If a is equal to 15, b is equal to 10, our previous example, this one, how will this set S look like? So S will contain all elements of the form, all numbers of the form 15x plus 10y, as long as the value of 15x plus 10y is greater than 0 and x and y are integers. So what does it mean? This is a specific example that I'm giving you so that you understand the set S. So for example, we can have x equals to 3, y equals to 1. So then this will be 45 plus 10, which is 55. So this is greater than 0 and x and y are definitely integers. So S will contain 55. What else will S contain? Well, maybe you can put x equals to 4, y equals to -2. Maybe that also works, because this is my x, this is my y. The only condition is this sum should be greater than 0. So this is 60 minus 20, so this is 40. So 40 is also inside this set. So like this, we plug in the value of x and y, check if it is greater than 0, and then put that number inside this set. This is how we are creating this set S. Okay. So, question, and this is again in the quiz section as well as in the comment section if you are not in the portal, that can you find few more numbers, few more members of S, provided A is equals to 15, B is equals to 10. Maybe you can find it. Let's see. Okay. So what can we say about S? Well, S for once contains positive integers by definition, right? So this is where we will use the well ordering principle. What is the well ordering principle? Well, it says, roughly it says that every set of non-negative integers contains a least element. This is apparently not so powerful, because of course it kind of looks obvious, right? If you have a bunch of positive integers in this set, there must be one which is the smallest one, right? There has to be a smallest one. That's the essence of well ordering principle. But just to point out at this step of the problem, that not all numbers or sets of numbers are well ordered. Any set which has this property that it has a least element is known as well ordered. Now, not all sets of numbers are well ordered. I'll give you an example. If you take numbers like this, 1 by 1, 1 by 2, 1 by 3, 1 by 4, 1 by 5, and so on. This goes on forever, and 0 is not here in this set. Let's call this set M. This set M does not have a least element. So rational numbers are not well ordered. Here integers are, positive integers, non-negative integers are well ordered. So we can say this principle. But rationals are not. So M does not contain a least element. Here is an exercise. Can you rigorously prove this? Rigorously prove that the set 1 by 1, 1 by 2 does not contain a least element, a smallest number. Can you prove this? If you are in the Chinta portal, then upload your answer in the assignment section. Or you can write, if you're in YouTube, you can write it in the comment section. Okay. So now, let's look at this. We will assume that well ordering principle works for non-negative integers, which we know it does. So S has a bunch of elements like this, ax1, by1, ax2, by2, and so on, such that axi plus byi is greater than 0 and xi, yi are integers. And suppose D is the smallest element of S. Our goal is to show that this D, the smallest element, is the GCD of AB. This is not a coincidence. The smallest element of this set S is D, that GCD. So this is our claim, and in the next part of this lecture we will be proving this, and we will see an application of this in number theory. It might not be available in YouTube, it might be available only in the exclusively in the portal. Anyway, keep trying beautiful problems, and we will meet in the next video.